quantum entanglement was discovered by Einstein, Podolsky, and Rosen. Podolsky was Einstein's assistant when he defected from Germany to the US, and Rosen was his assistant. Podolsky was a postdoc at the Institute of Advanced Study, and they wrote this epic paper in which Einstein tried to understand some aspects of quantum mechanics, which was quite new at the time, and found this paradox that became known as the EPR paradox. It led to two things. One was Podolsky, who was this very junior researcher at the Institute for Advanced Study and a postdoc, and needed to get a job afterwards, was very excited by this result, the EPR discovery, and happened to leak their result to the New York Times. The New York Times splashed it over the front page and said Einstein discovers problems with quantum mechanics. Quantum mechanics is quite new at the time. Quantum mechanics is quite new at the time. I like that, it's lost screen. Quantum mechanics was quite new at the time. Well, there were a couple of things that were new at the time. One was quantum mechanics. The other one was the idea of journals publishing things by peer review. Right? So today we all recognize that you send a paper to a journal, they send it off to your peers evaluate it and decide whether they get published or not. So back in those days, basically, if you discovered something and wrote a paper, you send it off to some esteemed scientist who then communicated it to the journal, and if they believed it, then it got communicated to the journal and published to the journal. So the leading journal at the time was in the United States was a journal called Physical Review, and they had just decided to switch to this whole peer review system. So that was the one thing. So the other thing was Podolsky, who needed this job and knew that he was writing this paper and discovered something really deep about quantum mechanics with Einstein, leaked their results to the New York Times and splashed it on the front page, really pissed off Einstein. So Einstein never spoke to Podolsky after the discovery of quantum entanglement. But they did send their paper to Physical Review, who, as per their policy, had sent it off to the reviewer, and then imminently informed Einstein that it had gone to a colleague in Princeton who was going to review this. Einstein was like, who the hell told you to send it off to somebody when I didn't authorize it? I will never publish in the Physical Review again. So he didn't. So this is an epic paper for a number of different reasons. But I want to talk about the mathematics underpinning quantum entanglement, because it's researched in the last couple of years in the context of things like quantum information, our current understanding of black hole physics, and in particular things like quantum computing. So the idea of entanglement is central to quantum mechanics. It's not a consequence, it is the foundations on which the quantum world, I wanted to say quantum realm, but I stopped. The quantum world is different from the classical world. And it turns out that all of this is actually quite understandable from the perspective of just knowing the mathematics that we've been talking about in the last couple of lectures, namely tensor products and tensor product spaces. So this is a very watered down version of what it means, what quantum entanglement means. But it's enough to, I hope, pique your interest, and if you are interested, to continue studying it further. So the first point I'd like to make is that quantum mechanics takes place in a vector space. In fact, quantum mechanics is all about linear algebra. If you don't believe me, then the best source to go and look this up is John von Neumann's epic text, the mathematical foundations of quantum mechanics. Quantum mechanics is linear algebra, okay, at the end of the day. So quantum mechanics is linear algebra. Taking place in some vector space and in most cases the quantum mechanics problems that we solve, like the harmonic oscillator or the hydrogen atom, the vector space that we're talking about is an infinite dimensional vector space, and the key point about it is that it's equipped with some inner product. Right? So we've talked about the inner product in the last couple of lectures, and some bilinear map of the vector space times the vector space is the real complex of the numbers. In quantum mechanics, it turns out that the field over which we work is necessarily complex. But that aside, quantum mechanics is linear algebra that takes place in a vector space. That vector space is typically infinite dimensional vector space, equipped with some norm. And in this context, it's called a Hilbert space. We'll call this vector space H. And states, quantum states in that Hilbert space are typically vectors in the Hilbert space. And technically, it's not. We'll come back to this in a little bit. They're not vectors in the Hilbert space. They're actually arrays in the Hilbert space. So complex. So quantum mechanics typically takes place not in the Hilbert space, but in a complex projective space. What these things are, we'll define a little later. So I want to tell you what I want to focus on in this line of thinking. So quantum entanglement is about states in this Hilbert space that are fundamentally tied to each other in some way. Okay? The thought experiment that Einstein, Podolsky, and Rosen used was, if I prepare a state, let's say the state can be characterized by some quantity which I'll call spin, and the spin can be either up or down. Right? These are physical things. Actually, it turns out you can take an atom, like a really large hydrogen atom, a Rydberg atom, and freeze it so that it only has 1 degree of freedom, and that degree of freedom is its spin, it's either up or down. Right? So you can do this in a lab, not just a thought experiment. So suppose I have a state in the Hilbert space that I'm going to call either up or down. The key point is that it's binary. Right? And I prepare two of these states. One is up and one is down. And I prepare them, and then I blast one of them into space, and I blast the other one into space in the opposite direction. And I have an observer observing one of the states very far away in that direction, and another one even causally disconnected, meaning no signal from this guy can get to this guy. Right? The point is that with the EPR paradox, and why it's called paradox, is because you can prepare this thing in some superposition with these two states. The one makes an observation and says, oh, it's down, and automatically knows that the other one has to be up, even if they can't communicate to each other. So that's the paradox in some sense. So the point is that I have these two states, these two vectors in this Hilbert space that are inextricably tied to each other. Okay? I would like to ask, mathematically, what does it mean to be inextricably tied to each other? And when can we disentangle states in the Hilbert space? So we'll come up with a set of conditions. Well, we'll first pose this problem as a mathematics problem about tensor products of vector spaces, or tensor products of this Hilbert space. Then we'll ask, given a state, given some state in this tensor product, when can I disentangle these states? Okay, when can I factor it into two states? This factorization problem is what's called the Segre conditions, and we'll come up with a set of conditions which are basically linear algebra conditions that said, given a particular vector in this tensor product of the two vector spaces, when can I factor it into a vector into one space and a vector that lives into another space, lives in the other space. Okay, so that's basically where we're going with this. All right. So to that end, let me ask the the following. Let me set up the following problem. So suppose if we take for granted that quantum mechanics is linear algebra taking place in some vector space, which we're going to call a Hilbert space, and quantum states are vectors in that Hilbert space. That's just because I'm acknowledging that there's some fine print to come. But for now, you can think about them as vectors in the space. Okay. And I'm going to use for this section physicist notation for vectors in a vector space, which comes from Dirac and Dirac's Bra-Kent notation. So this is a column vector. This corresponds to a column vector, psi 1 to psi n, and the corresponding row vector is called the Bra vector, and this corresponds to psi 1 to psi 2. And they combine together, the Bra and the Ket combine together to form a bracket, and the bracket is the inner product between these two. So what mathematicians would say, psi transposed psi. Okay. Okay. So that sets up the basic terminology for us. Now, suppose I have not one of these spaces, but I have two spaces. So suppose we have two vector spaces, two Hilbert spaces. And I'm going to partition our system into two parts, A and B. With Hilbert space HA for part A and Hilbert space HP part B. Okay. And just for ease of explanation, I'm going to assume that these Hilbert spaces are finite dimensional. So we're working with finite dimensional vector spaces, which means I don't have to deal with integrals, I have to deal with sums. That's basically what it means. Okay, but the argument still holds. So these are finite dimensional vector spaces. I'm going to denote the respective bases for each of these vector spaces by NA and NB. So NA is the vector space for is the basis for the vector space HA. NB for the Hilbert space HB. And NA, comma, NB will correspond to the combined Hilbert space that I need, which is HA tensor HB. Okay, so I have two vector spaces, A and B, HA and HB, and I have a combined space which I'm going to form by taking the tensor product of HA and HB. I denote the basis in the A space by NA, and the basis by in the B space by NB, and the combined space I'm going to label the basis by NA, comma, NB. Okay. A general vector in this space, in the tensor product space, we call it psi, and in this notation, psi is usually written as the sum over NA and NB and A and B and A and B on the side. I'm going to unpack this for you now. Okay, so this is an expansion over a set of basic vectors. There's the basic vectors. This is the part. This is the component of psi in the basis vector NA and B. Okay, this is the notation that you will find if you pick up any book on quantum computation or quantum mechanics, and you look for an expansion of a general vector in the tensor product space in terms of the basis of that tensor product space. Let me show you that this is exactly the kind of quantity that we've been talking about just now. So the reason I introduced the idea of tensors and tensor products and stuff is precisely so that we can take a language like this and translate it into something that's more familiar. So in our language that we've been developing so far, we would identify this guy with the vector psi. Okay. So what we were calling vectors, that's what it would be. This guy here we would have called psi and A and B. So psi, two indices upstairs, and A and B. In other words, something that behaves like the components of a rank 2 tensor of type 2,0 that we get by taking two vector spaces and tensoring them together. And then this guy here is what we would call EA, or rather say A and A tensor product E B and AB. So in the language that we've been developing with tensors and tensor product, that is how we would phrase exactly the same thing. We've seen this before. You take two vector spaces, you tensor them together, you will get a tensor product space. The components of a general, this would be a vector, it would be a tensor. Or technically, I guess I should drop the arrow. So this would be a tensor of rank 2, type 2, 0, meaning that its components look like this, and the basis for the tensor product space looks like that. This is exactly the kind of thing that we've been talking about in the last couple of lectures. Okay. So far, I've introduced new notation and maybe some new words, but conceptually, nothing particularly new that we haven't seen in the last one. Okay. So suppose that I go a little further and try to do something new. The new thing that I want to do before. So I'm going to phrase everything now in the language that we've been working with so far, and ask the following. Suppose I have a finite dimensional, suppose I have some finite dimensional space. Suppose that EI1, I think it's one I runs from 1 to n is a basis for the Hilbert space H1 and EI2. Set EI2, we're now let's start this with we're going on 1 to n is a basis for H2. Then the following is true. The dimension of H1 tensor H2 is n times n. So if I start off with an n-dimensional vector space and an m-dimensional vector space, the tensor product produces an n times n-dimensional vector space. Okay. Now, in addition, suppose I have some vector in this vector space, some general statements in the vector space that I'm going to write as psi ij e 1 I tensor e 2. Okay. So I'll use a capital to denote the state or vector in this tensor product space, and I'll use the corresponding lowercase Greek letter to denote the components. Okay. So here's the point of it. If we can find some x in, let's say x equal to x I e 1 I in h1 and y to yj e2j in h2 such that our general vector psi can be written as the tensor product of these two vectors x and y, or in terms of components that this is xi yj e I 1 e j. In other words, that I can factorize this guy psi ij into the product xi xj, then psi is called decomposable. And two states that I'm working with, x and y, are unentangled. If I can't find any such x and y, then I can't factorize the state into x tensor product y, then these two states are called entangled. So quantum entangled states are states for which you cannot factorize these states. Okay? Is that clear? Set up as a mathematics problem, right? I start off with some Hilbert space H1 and another Hilbert space H2, and I know what the tensor product is, I extract that. Then I go to the tensor product space and I find some general state psi. I can generally expand the state like this, and the basis for the tensor product. And I ask, can I find an x in H1 and a y in H2 such that I can write down psi as a tensor product, which necessarily means that the components of psi ij factorize in xi times xj. If I can, then these two states x1 and x2, these two states x and y, the relatively different vector spaces are unentangled with each other. If I can't, then they are entangled. So that's fine as a definition, but it's a bit too vague in order to be practical.
Sorry. So the two vectors x and y always make the dense product.
Yes.
I mean, if we vectors are unentangled.
No.
So that would derive like some other vector psi.
No. So the point is that if I can take this psi ij is made up of tensor, right? Then they're not entangled. If I can't do it, so then the negation of that state, then they are entangled. So tensor products of two vectors are not entangled.
Yeah. But so that same x and y are unentangled with respect to psi.
With respect to psi.
Yeah.
Right. Okay. So the question then becomes, when can I decompose a general state psi? So given some general vector in a tensor product space, can I come up with conditions under which I can decompose it? And if those conditions are not met, then I can't decompose it, in which case it corresponds to an entangled state. So the question then is, under which condition, under what conditions can we decompose a general state psi? Okay, so this is really just a question about tensor product space. So let me treat the whole problem like this. So I'm not worried about quantum mechanics at this point. I'm going to ask this question as a question in linear algebra in this product space. Okay. So suppose that I do indeed have this structure. So vector space H1, vector space H2, some vectors that live in that space. Some tensor product space, in which case I can fix some general state in that tensor product space and expand it to the basis by tensor product J, EI tensor product EJ, with some psi. So now suppose that indeed I can find some x and some y in the factor spaces, such that I can write psi ij as xi and xj. Okay? So I'm going to ask a question like this. How many components does, if this is an n vector, this is an n vector, how many components does this guy have? So I runs from 1 to n and j runs from 1 to n. It's an n by n matrix, and it's got nm components. There's an nm dimensional space. However, these guys are just n of n and n of n. So I'm going to get a maximum of n plus n components out of this guy. For this to be true, for this factorization to work, I need to have psi ij satisfying some constraints that take me down from nm to n plus n. Okay? So we're just a counting problem. So since psi ij has nm components and xi yj has n plus m components, we need psi to satisfy some constraints. Question is how many? Okay, so to decide how many, let me pick some. Okay, I and j run from 1 to n and 1 to m respectively. So let me pick some P and Q. Such that psi PQ is non-vanishing. Okay. And I'm going to leave for you guys to discuss the case where we can't find any such non-zero matrix elements of psi. So psi has all zero matrix elements. It's a trivial case, but it's one that you think about and convince yourself that you understand what kind of. I'm going to do the I can always find some P and Q, and that P and Q will correspond to some non-vanishing matrix element of psi I j. Okay, so now suppose I have this non-vanishing matrix element. And we're going to assume that xp yq is psi pq for this fixed value of p and q. So for this fixed matrix element, I'm decomposing it into some xp times yq. Okay. So the fact that this matrix element is non-vanishing necessarily means that the product xp yq is non-zero. So now if I take the n plus m minus 1 entries that I get by taking xp and multiplying it with yj, for all j going from 1 to m, and union with xi yq, and I goes from 1 to m. The remaining matrix elements are all fixed. And they're fixed because I can completely determine them. Sorry, this is I not equal to P and Q not equal to J. So I not equal to P, J not equal to Q. So I completely determine all of the remaining matrix elements because I know that I can write xi, yj as xi, yq divided by xp yq times xp y. Yes. Or equivalently, I can write psi ij as psi q divided by psi pq times psi pj. In words, what this says is that in order for the equation psi ij to be factorizable into xi xj, that or rather, in order to solve the equation psi ij equal to xi yj, I need to or I can freely specify the psi IQs and the psi PQs, and then fix all the elements with respect to that, to this equation. Yes. Yes. In other words, psi must satisfy NM minus N plus M minus 1 is N minus 1 and M minus 1 constraints. That tells me how many constraints my vector in the Taylor product space needs to satisfy, how many conditions it needs to satisfy in order to be decomposable or not. Okay. Let me pose this in a slightly different way, and then I'll finish up next time. So suppose I have again, just to keep in mind what we're trying to do, given some general psi, I want to know when I can decompose psi into a tangent product of x and y. So suppose like that. So what this means is that psi lowercase ij is xi yj. But this is some set of equations. I'm asking, does the set of equations have a solution? And I've given you some conditions on when it may have a solution, but I haven't really constrained this in terms of the components. Let me see if we can do that. So assuming that this has a solution, that means in terms of the components that psi ij is factorizable into xi xj. So this must hold for psi ij, but also for any of psi, let's say KL, psi IL, and psi AJ. If I can find a solution that decomposes like this, let's hold for any combination like this, or fixed K and L. In which case it follows that psi ij, psi L is just xi. Yeah, xi yj, xk yl, and now if I shuffle these guys around, this is the same as xi yl because these are normal multiplication. X K yj, or in terms of the components of psi minus L, psi k j. So I need psi I psi j equal to psi I j psi kl equal to psi il psi kj, which is the same as saying the determinant of psi ij psi il psi kj psi kl equal to 0. For all I, j, k, and l. So there's a condition that is a concrete condition on the components of the general state psi that must hold. It's a necessary condition, but it turns out it's also sufficient as well. And in the next lecture, I'll prove that it's a sufficient condition. But at this point, it is a necessary condition that needs to hold if this is to be decomposed. If it doesn't hold, then we have an entanglement. Okay. And again, this is technically quantum mechanics, but in practice, it's just linear algebra. It's just things to do with matrices. Okay. Next time, I will finish this off by showing that this is a sufficient condition, and in coming up with a sufficient condition, we will write down a set of conditions called the Segre conditions, and as long as the Segre conditions hold for any general state like this, I will always be able to decompose it into factorizable states, and if I can decompose it into factorizable states, then they're not entangled. Okay. All right. Any questions?